Section 6, Entropy and Gibbs function. Just as we needed a special treatment for enthalpy in reactive systems, entropy also requires a special approach, and this is where the third law of thermodynamics comes in. For non-reacting systems, we only ever needed entropy differences. The arbitrary datum in the steam tables cancel out, but for reactive systems, just like with enthalpy, substances enter and leave and the datum doesn't cancel. We need absolute entropy values. Entropy measured from a universal zero, the third law of thermodynamics gives us this zero. The entropy of a pure crystalline substance is zero at the absolute zero of temperature, which is 0 Kelvin. This is not a definition like our enthalpy datum. It's an empirical observation from experiments. At absolute zero, a perfect crystal has only one possible microscopic arrangement, no disorder, so its entropy is zero. Here is a very important warning. The steam tables A4 through A8 and the other gas tables A7 through A18 do not give absolute entropy. They give entropy relative to an arbitrary reference, so you cannot use them directly for reactive systems. Instead, use table A25 for absolute entropy at the standard state, 298 Kelvin at 1 atm pressure, or table A23 for absolute entropy of ideal gas as a function of temperature at 1 atm reference. For an ideal gas at temperature T and pressure P, the absolute entropy is given by equation 13.22, which STP is equal to ST at 1 atm minus R ln P over P reference. For a component I in an ideal gas mixture, equation 13.23, SITP is equal to SIT minus R ln YI times P over P reference, where YI is the mole fraction of component I and P is the mixture pressure. The extra term with the natural log accounts for the fact that mixing adds entropy. A component in a mixture has a lower partial pressure than a pure gas, so it has higher entropy.